All right, everybody. Thank you so much for being here at our afternoon seminar today. My name is Cinnamon Moffat, and I'm going to be your host. This is a hybrid event, and we have folks online and folks in the room. So, welcome to you both. Just a couple of logistics, and then we'll get rolling because I saw how many slides Dan has, and I want to give him some time to share with you. But for folks online, if you haven't been with us before, please put any questions you might have into the chat box. We have a volunteer here, Roseanne, who will make sure those questions are addressed or asked to today's presenter. So please feel free to engage with us that way. But your cameras and mics have been disabled for today's event. For folks in the room, if you haven't been here with us before, when you get to the place where you're ready for a question, if you just raise your hand, I'll bring you the mic. And that way folks online can hear and our speaker can hear. So that's how we kind of run our hybrid event. So please make sure that you raise your hand and I'll make sure you get your mic. Wanted to make one quick announcement. We're getting close to the end of the year, everybody, but we have one more seminar on December 18th. We have Catherine D. Rivera, who is a professor at Portland State University, who's going to be coming and giving us an update on the green crab status along the coast. So Sylvia Yamada has been working with us often on that. Catherine has been partnering with her, and so there's been some updates that I have heard at State of the Coast, and so some things that will be really interesting to be shared here. But for today, I wanted to introduce our speaker. Dan Hellin is the director of PacWave. His role provides strategic leadership and development and operations for that site, advancing PacWave's mission to accelerate wave energy and innovation through real-world testing, reliable demonstrations, and commercialization support. I have a hard time with that word. With over 30 years of experience in managing complex coastal and ocean projects worldwide, Dan brings a wealth of experience and expertise to marine energy, environmental assessments, policy development, infrastructure planning. And so he's going to give us an update on the PacWave project. And so I'm going to hand it right off to you, Dave. Got your
Yep.
screen? Awesome. You want to do a little test? Can you all hear him?
Yeah, can you all hear me okay? Perfect. Well, thanks very much, Cinnamon. Yeah, I'm Dan Hellin. I'm the director of PacWave, which is a wave energy test facility located off the coast of Newport here. But before I start talking about PacWave, I just want to sort of talk a little bit about why we're even talking about wave energy. People know about renewable energy. Wave energy is not one that springs to mind when people are thinking about renewables. And there's a reason for this. I'm not going to have a lot of graphs. Most of it's going to be pictures. And really the point of this graphic is just to show, you've got your more traditional forms of electricity generation, coal, gas, and so on. And then you start, as you move up, you get into hydropower, you get into wind, you get into solar. There's a little bit of biomass up there at the top. And then right up here, this tiny little green line that really can't be seen at the top is other renewable energies. And that's where wave is buried in amongst those. Looking at this at a slightly different way, and again, the numbers aren't really important here, but what you have is the sort of different scales of renewable energy. So solar here listed as 1.8 million megawatts. Wind, a lot of wind, most of that shore-based wind, but a lot of offshore wind as well. And then dropping down a whole order of magnitude to sort of bioenergy and biomass at 150,000 megawatts, dropping down another order of magnitude down to geothermal, and then dropping significantly down to marine energy, which includes wave energy. But the amount of commercial wave energy at the moment in the world is absolutely tiny, a couple of megawatts, and that varies depending whether there's a device in the water or not. So maybe enough power to power 1,000 homes, which is really remarkably little. The reason we're interested in wave energy, it has huge significant potential. There's been lots of studies about the theoretical amount of energy that could be produced from waves, and a number that's thrown around is around 60% of the power used by the US could theoretically be generated by waves off the coast of the US. So that's something that is worth considering. It's also the density of waves. If you've probably all been in the ocean and been hit by a big wave. There's a lot of power in those waves. Waves are carry or hold up to 5 to 10 times the power of wind and 10 to 30 times the power of solar. So again, huge potential there. And wave is also very complementary with both wind and solar, and it's also incredibly predictable compared to some of these other forms of renewable energy, which is really important when you're looking towards kind of base load electrical power generation. So this graphic's just sort of showing wave energy across the world, and the orange is where you've got the most wave energy. Up in the northern hemisphere, basically wave energy is the greatest on west-facing coasts. So the Pacific Northwest and Canada, Northern Europe. There's also a lot down in the southern hemisphere, as you can see. But one of the critical things if you're trying to turn this power into electricity is you want that electricity to be near where the demand is. If you're generating electricity and having to put in, hundreds of miles of transmission lines, that's incredibly expensive. So the beauty of the Pacific Northwest and Northern Europe and so on is you have this wave energy that is just off the coast. This is a somewhat complicated graphic, but it illustrates a couple of things. So really the kind of turquoisey blue is the wave energy that we're looking at. And you can see places like Hawaii and Alaska have huge wave energy potential. But the issue is there isn't really the demand there. On the East Coast, a lot less because it's an east-facing coast. But the West Coast, all the way down from, on this because it's the US, but all the way down from Washington down through California, a lot of potential for wave energy, greater potential in Washington and Oregon than in California. So one of the questions is why is wave energy, why are there such sort of tiny amounts of commercial wave energy at the moment? And there's a number of challenges here to the development of wave energy. One is there is very little testing infrastructure. This is a relatively new technology. There's not a lot of places where you can test full-scale, open ocean, grid-connected power generation, which is critical if you're developing this type of technology. There's also a lack of convergence in the technology. I sort of point at wind. Wind turbines or windmills have been around for a very long time. Wind turbines are far more complex than that, but the basic concept is the same. With wave energy, there are a lot of ideas out there still at the moment about how we might be able to capture the energy in waves. And we haven't got to the stage where we've proven that some of these technologies are better than others. So there's a lot of ideas, and until we can actually test them and show what actually generates the power, what's economic to run, what has low operation and maintenance costs, until we can do that and the technology can narrow down to a few technologies that are proven to work, it's really difficult for the industry to advance. Costs and timeframes of developing any sort of technology associated with the marine environment is very high. You also have the fact that other renewables like wind and solar have become very, very cheap. So you're trying to develop another renewable energy source that's, way behind those, and at this stage is still very expensive. There's also, because there's been very little wave energy, very few wave energy devices deployed, there's perceived environmental uncertainty. What's going to happen when we put these devices in the water? And until you can get more steel in the water, as we say in the industry, more devices deployed, more environmental monitoring, people are going to have these concerns. They're justified, but you need devices in the water to do the science, to gather the data. There's also the fact that there's a lot of federal and state agency jurisdictions and regulations that were not written with wave energy in mind. A lot of the regulations were originally developed for oil and gas, have been adapted for wind and solar and so on, but no one's been thinking about wave. And then because of this and many other things, there's been limited public and private investment so far. So that's where PacWave comes in. So what is PacWave? So we are a pre-permitted, grid-connected wave energy test facility. We are the only test facility of its kind in the US and one of about 8 or 9 in the world. So we're a very, very unique type of facility. And what we offer is the support for the testing, research and development, and demonstration of wave energy systems, wave energy devices or wave energy converters, or we call them WECs, and other innovative technologies associated with wave energy. So the primary mission of PacWave is to support the national and international marine energy industries on their path to commercialization. We have some secondary missions, which is to enable the development, prototyping, and testing of other types of marine technology, and also supporting research that's going to help the marine energy industry. And PacWave has been developed and is operated by OSU, and has been primarily funded by the US Department of Energy. And part of what we're trying to do is address some of these challenges. The ones shown in green are the ones that we think PacWave can help. Obviously, providing the infrastructure as we get more steel in the water, more technology tested and demonstrated. The certain technologies are going to come out as the more obvious ones, the best technologies for wave energy. And all of that is going to bring down the costs. As we start getting more devices in the water, costs will come down. Conducting environmental monitoring around devices is going to help deal with some of the environmental uncertainties. And part and parcel of that is going to lead to more streamlined permitting, is the hope. And then as the belief in marine energy and wave energy increases, this expectation is that there'll be greater investment in this. So that really brings us to what PacWave is. So as I said, we're a wave energy test facility located off the coast. The map on the left is very familiar to all of you. The map on the right shows that we have 2 sites. We have PacWave North. We're not very original with our naming. PacWave North is north of Newport. PacWave South is south of Newport. PacWave North is a non-grid connected site. I'm not going to really focus on that. PacWave South is our flagship site. This is grid connected, which is illustrated by the dotted lines, which are subsea cables running from the site to shore. The location of the site was chosen by the local fishing community. And the site itself is divided into 4 test berths, as we call them. So 4 cables, 4 test berths, 4 different companies can come in, 4 commercial companies can come in and test their technology out at the site, and then send power and data back to shore through the cables. This is just a conceptual drawing of illustration of what PacWave is about. So we have devices offshore being tested, connecting to our cables here through these connectors on the seafloor. We have environmental monitoring going on around the testing. Then we have the cables running to shore and running to what we call our utility connection and monitoring facility, which is really our shoreside substation and control center. And then the power going on to Central Lincoln PUD's distribution system. So critical for this testing of devices for these technologies is that it's grid connected, power is going onto the grid. They're proving that these devices can actually function and, you know, in the real world, start powering homes and businesses locally. So this is the timeline. You may have heard of PacWave. You may have heard of PacWave for quite a long time. We've been working on this for quite a while. We started off with the original site selection process back in 2011, 2012. That's when Newport was selected. And then the sort of yellowy color is where we got into our permitting process. So we had 8 years of permitting, which was a very long time. I started on the project just at the beginning of that permitting process. And the permits culminated in 2021 with two of the big federal permits. So we have a lease from the Bureau of Ocean Energy Management, BOEM, who you're probably familiar with the discussions about offshore wind. And then we have a license from the Federal Energy Regulatory Commission, or FERC, and that's what gives us the authorization to put power onto the grid. So with securing those 2 sort of final federal permits, kicked us into the construction phase, which is in blue, which ran through 2021 through to actually beginning of 2025. And I'm going to talk more about that. And then now we're just getting into the operational phase. So the last 12, 14 years that we've been working towards this, we're now actually getting to the stage where we're preparing to do what we've been working towards and planning to do for a very long time. So I want to walk you through a bit of the construction because for those of you who are local, you've probably been impacted by some of it over the years. But it has been a really pretty phenomenal and challenging construction process. Very, very different to what the university is used to on construction projects. But we have three real phases. The first is what we call here, which is the underground construction, which was focused on installing underground conduits through which our cables were later installed. And I'll talk more about all of these. The second phase was our terrestrial construction, which was the construction of our utility connection and monitoring facility, or UCMF, which is located in Seal Rock. And then the third phase, which was by far the most complex and costly phase of the project, was the installation of our subsea and terrestrial cables. And I'll talk more about that. But those lines that you can see out in the ocean there is about 47 miles in total of subsea cables that were installed last year. So underground construction. So our cables come in at Driftwood Beach State Park in Seal Rock, which is shown here in yellow. And the underground construction was really focused on the installation of these conduits. So we have these blue lines here are four conduits that run from Driftwood out through the nearshore area. And these run, you probably can't see it very clearly, but these conduits were installed running down about 120 feet down underneath Driftwood Beach, underneath the nearshore area, and then punching out in about 45 feet of water on the seafloor. And these are installed using horizontal directional drilling. You may have seen sort of ditch witches on the side of the road doing utility conduit installation. For what we did, we basically had supersized ditch witches. And this is a picture taken by the local newspaper at the time in July of 2021. And this is Driftwood Beach State Park parking lot. We took over the whole parking lot, and we have two very large drill rigs that were basically boring holes underneath the seafloor into which we then installed conduit. And this is a ground level view of those drill rigs. Busy doing their work. And then the bottom pictures are all the conduit that we installed. So this was 10-inch steel pipe that came in. The second picture from the left on the bottom came in lengths of about 40 feet, each of which weighed about a ton. So after they drilled the hole under the seafloor for each of these bores, they pushed this pipe in one length at a time, threaded it together, pushed in another length. And as I mentioned, the offshore bores were about a mile long. So by the time you were pushing in the last of that pipe, you were pushing in a mile of pipe into the hole, which was pretty impressive from an engineering standpoint. Took several months to do those bores and get all the conduit installed for the offshore bores. And then what we did, this shows Driftwood, and it shows the location of our UCMF just down the road. Basically, we flipped the drill rigs around and then bored between the UCMF and Driftwood to install conduits between those two locations. So we went under Driftwood Beach State Park, went under a number of private properties, under Highway 101, under a couple more properties, and then punched out on our property on Northwest Wenger Lane. And this is one of the drill rigs turned round, just to give you some idea. That's a person standing there, just to give you an idea of size of these things. Pretty large pieces of equipment and quite specialized pieces of equipment. Once we had all the conduit installed, the next piece we did at Driftwood was basically building a very, very large splice vault. So we have offshore cables coming into the splice vault on the seaward side, and then the splice vault is really a transition from the very, very expensive offshore cables to slightly less expensive terrestrial cables. So this vault is 74 feet by 16 feet, 10 feet tall. and basically was built underneath Driftwood Beach State Park, under the parking lot. So what you have, if you go to the parking lot now, you will see a series of 5 manhole covers in the center of the park, down the center of the parking lot. And that's basically all you can see of the work we did. Other than a lot of improvements that we did, part of our deal for shutting down a state park, shutting down the parking lot of a state park, we maintain pedestrian access, but part of it was rebuilding the parking lot, building viewing platforms, sidewalks, fixing their stormwater system, and so on. So that work took just under a year. We installed in total about a little over 6 miles of conduit, 1.2 million pounds of steel for those offshore conduits. The second piece of the construction was the build of our utility connection and monitoring facility. So these are the conduits from Driftwood coming into a splice vault in the parking area. And then we have 3 buildings, power conditioning building, as we call it, and I'll talk more about this. A switchgear building, which is basically much like a substation, and then a control building. And one of the things we had is, I mentioned before, we had 4 test berths offshore, each with their separate cable. And the whole idea of this is when we have people testing, companies testing, they're competitors. They have intellectual property concerns and so on. So the cables that they have running from their test site remain completely separate. All the power, all the data, everything running through their cable remains completely separate until it terminates in one of the developer bays in this power conditioning building. And that's secured space for the companies. So basically their system is completely separate from everyone else's, which is really important for commercial companies who are developing this technology or these technologies. So this is what the facility looked like a couple of months ago, after a couple of years of construction. It's about a little over 18,000 square feet of interior space within these 3 buildings on a 1.5 acre site. Because the site is technically a substation, we're potentially dealing with 36 kV power, so 36,000 volts. For some of these may be generated in the voltage coming back to shore. So this is a substation to all intents and purposes, which is why it's surrounded by a 7-foot high chain link fence, and also has CCTV and alarms and so on, much like the substations that you have with Central Link and PUD. We're really trying to discourage people from going into that site because it is, 36 kV is not something you want to mess around with. So this just shows one of the developer bays in the power conditioning building. The idea of this is our FERC license is for 25 years. So we've tried to design a facility looking forward to what developers may need in the next 25 years, which is pretty close to impossible. But talking to other test sites in the world, one of the things they said to us is, if you've got space, build it big. Give people a lot of room because they'll probably fill it. So we designed the bays in this power conditioning building around the idea that potentially companies would have their equipment containerized and they can back 2 40-foot containers into their bay, which is probably more than anyone is ever going to need. But last thing we want to do is have people short of space. At the back of the bay is where the cables come in. So this is actually, I've said each of the developers, their cable comes into their space. So these are the cables, the individual conductors coming in for the cables from Driftwood, all the fiber optics, and there's a lot of fiber in these cables for data transfer coming in here. And then basically the idea is they can install their equipment. The power that they're generated needs to be cleaned up. As you can imagine, if it's a wave device, it's going to be surgy power. I'm not an electrical engineer, but basically that needs to be cleaned up before it can go onto the grid. It needs to be conditioned. So the developers will install equipment there to monitor and condition the power. And then it basically runs to our switchgear room. And here we have pretty standard medium voltage switchgear, as you would find in a substation. We have a DC battery backup system. And then in these black cabinets is basically all the metering and relays to do for each of the companies. So we have a quadruplicate system here, so one for each of the bays. Each of the individual companies, their power is metered separately, so they know exactly how much power they're generating. They're going to need that for investors and everything else. Again, it's keeping their data separate. We're not intermingling anyone's data until the power is ready to go on to central Lincoln. Then it all comes together. We have our own PacWave metering equipment here, our what's called supervisory control and data acquisition SCADA system for monitoring our equipment. And then the final cabinet that's shown here is central Lincoln PUDs, relays, and metering system. So ultimately, that's what's telling them how much power is going on to central Lincoln's system. And then the final building is our control building. This is slightly more livable space. The other two buildings are pre-engineered metal buildings. This is a wood frame building. And we have individual secured monitoring rooms for each of the developers. But we also have things like some meeting rooms and restrooms and so on to give them some type of, creature comforts. It's not a luxurious facility, but it will function, and it is quite nice. This was designed by HGE architects out of Coos Bay, who not only were wonderful people to work with, they also did a fantastic job on the design. So the front end of the space, we do have a lobby and a small conference room, which will be, the site isn't open to the public, but if we are giving tours or showing people around, these are the areas that will be accessible to people who are not the developers or our team. But the rest of the facility is pretty much secured, partly because of the fact that they've got proprietary information and data coming in, or you've got medium voltage power. Each of the developers has a pretty simple monitoring room where they can install all monitoring equipment. In reality, what's going to happen is these companies will be testing their devices for 1, 2, 3 years, something like that. They'll come to this location, they'll set up, they'll do some initial, monitoring, but then most likely they'll be monitoring and controlling their devices from wherever their headquarters are. That could be somewhere else in the US, it could be somewhere else in the world. And then we expect they'll periodically come back to do some maintenance and check up on stuff, and then ultimately decommission their equipment, move out, the next developer will come in. As I said, we also have a conference room, meeting room for them, and a break room. So we have a facility where these guys can set up. Our monitoring rooms intentionally are relatively small. If they want to have office space locally, they can go and rent office space. This is meant to be, basically a functional space that they can use to set up their testing. And if they're going to stay locally, then great, they can lease space. And then the final piece, as I mentioned, the biggest part of the construction project was the installation of our cables. This was led by a company out of Louisiana called RTKC. They were hired to source and oversee the manufacture of our cables. Our cables were manufactured by a French company called Nexans in their factories, primarily their factory in Norway, but also their factory in Switzerland. There were no companies in the US who could manufacture the cables we were looking for in the lengths we were looking for at the time. That may be different now, but I think it's still true, which is why we had to go with a European company. And then on the illustration graphic I showed that on the ends of the cables, there were some connectors. Those connectors, and I'll talk more about those, but those connectors were made in Denmark by a company called McCartney. And basically, those connectors were then shipped to Norway, terminated on the end of the cables. The cables were then transported to the US and then installed last year. So these are a couple of pictures from inside the factory. This is inside the factory in Norway. This is our cable actually being spun up. Here's a handrail, a guardrail, normal waist height to give you some idea of the scale of that piece of equipment. And here we have Giovanni Ganella, who was RTKC's European rep, standing on our stack of cables on the dock in Norway. So he's standing on a stack of 47 miles of subsea cable. And he's standing between two of our subsea connectors, a close-up of which you can see in the bottom picture. So basically, if you think of our cables like extension cords, we've got a plug on the end to allow other people to plug into. So we have half of a connector, which is the silver piece on here, and that's probably 4.5 feet long, 5 feet long, 6 feet long, something like that. And then the yellow segments you see are actually bend restrictors. One of the critical things with subsea cable is if you bend it too much, you damage the fiber elements and you damage the conductors, and this cable's really expensive. So everything about the cable installation that I'm going to talk about, one of the critical things is not allowing it to bend too tightly. So that connector with those bend restrictors on it weighs about a ton. And there'll be a reason. There's a reason I'm mentioning that. So last year's operations, you may have seen a number of these vessels offshore if you're local. We had a number of ships involved in the cable installation. First was the Frida up here, which was the 454-foot freighter that carried our cables from Norway to the US. And then the primary vessels that we had in the operations offshore were the Innovator here, which was the cable lay vessel. So when we installed our cables, we did it in two phases. First, the Innovator, the cables were pulled into driftwood through those conduits, terminated in driftwood, and then the Innovator laid the cables along the seafloor. And then the next vessel, the Nautilus, came in after that and then buried those cables into the seafloor from the end of the conduits, which are a mile offshore, all the way out to our test site, which is actually about 7 miles offshore, and our cable routes are, 10 to 13 miles. So the Nautilus did the burial, the Innovator came in beforehand and did the cable lay operations. And then we had a dive boat, dive and general support boat, which was a converted firefighting boat, the Liberty, 89 feet, had a commercial dive team, 4 divers, dive superintendent, recompression chamber on board. They were only diving on the end of our conduits. They're not diving at our offshore sites, the test site itself, because that's 260 feet deep. They were diving shallower, but because it was commercial diving, have to have a recompression chamber on board. And then this is just showing the route of the cables came from to get to the US. So they came out of Rognan in Norway, which is actually inside the Arctic Circle, which is a bit of a strange place to have a cable manufacturing factory, but there was some reason for it. So they were loaded on board the Frida in late May of last year, and basically then headed down to Port Fourchon, Louisiana, which is where the Innovator, the cable lay vessel, is located. The parent company, Hornbeck Offshore Services, all their vessels are based out of Port Fourchon. So basically, they got into Port Fourchon in mid-June and then spent the next couple of weeks transpooling those 47 miles of cable off the Frida onto the Innovator. And then they were meant to leave 1st of July, but there was a hurricane passing through the Gulf, so they got delayed a few days while the seas dropped before heading down to the Panama Canal, through the Panama Canal, and then up to North Bend, which is where they based their operations. And this is just a few seconds taken off a webcam. This is at the Miraflores dock, lock, which is the last lock on the Panama Canal. And the vessel in the lock at the front is the Innovator coming through, just about to head into the Pacific Ocean at the time, which was exciting for us to actually see our cables at least in the correct ocean at that point. So I'm not going to go into detail on this, but I did say that the operations for the subsea cable installation were complex. There was a lot going on last summer. We initially had what's called a grapnel run, which was the Liberty trying to clear any debris from along the cable routes, old crab pots and so on, derelict crab pots and line and chain, anything that was along the route that was going to cause problems with burial. We then had a shoreside crew that were doing installation of the terrestrial cable and then switched to helping with the subsea cable and then back to the terrestrial and all the cable terminations. And This was the innovator doing the cable lay operations with support from the dive crew. Once the innovator had finished its lay operations, we then did some secondary armoring for areas where we didn't get very good burial. We put what were called concrete mattresses over the cables to stabilize them, stop them moving around on the seafloor. And then once the innovator had done some of the cable lay, the Nautilus came in and did the cable burial. So the Nautilus was out there for about 2 months doing the cable burial operations. So this is the innovator fully laden sitting off driftwood before laying the first cable. I talked about the fact that you want to prevent the cables from overbending. So that's what this very large gantry over the top of this is the cable tank here, and I've got the next slide will show you it. But the cables, when it's being fed off the stern, comes up and over the top of this gantry and then down onto the stern deck and over the stern. And that gantry is really just to prevent that cable from overbending as it comes up out of the cable tank. This is just some additional pictures. So this is the cable on the innovator, the stack of cable in the cable tank. My desk was just in this little window here for these operations. You can see two of the subsea connectors strapped onto the side of the cable tank. Again, to give you a scale of this stack of cable, 47 miles of cable, and a cross-section of what the cable looks like, a pretty grubby cross-section. But the cable's almost 3 3/4 inches in diameter. So this is just an aerial shot of the innovator itself. And again, I'm not going to go into a lot of details here. The innovator it's not a cable lay vessel as such. It's an offshore support vessel, offshore supply vessel, a big open deck. And basically RTKC installed a huge amount of equipment on board, all associated with the cable installation. In this picture, the only piece of labeled equipment that is part of the ship is that large 40-ton crane. All the rest of it was installed by RTKC to assist with the cable lay operations. And then this is just some drone footage, and I do apologize if people either have vertigo or get seasick, but there's some people here to give you scale. This is the cable looping up over the top of the gantry, down onto the deck, through what's called a linear cable engine, which is basically some rotating wheels to help guide the cable off the stern, and then cable going over the chute on the stern. This is the control tower, and this is actually the ROV shack, the remotely operated vehicle shack. We had remotely operated vehicles on the seafloor monitoring all the undersea operations and doing some of the physical operations. So basically what the innovator did, the cables were fed off the stern, pulled through those conduits one at a time, secured in Driftwood Beach State Park, and then the innovator basically headed out to shore doing what's called laying away. And this is what this is basically very, very slowly laying the cable off the stern of the vessel out to the test site. And this shows the 4 cable routes going out to the test site. So we have driftwood here. The end of the conduits was about here. And then the cables looped out and up and around the back of the test site. And zoomed in here is the test site itself in blue. And the cables, this one coming in from the south, but all the others coming in and looping in from the west side of the site. And then the yellow dots you see are where we deployed those subsea connectors. So you remember I said those subsea connectors and bend restrictors weighed a ton. They were pre-terminated on the end of the cable. So you laid the cable out until you got to the test site. But then you had the issue that the connector was on the wrong side of that 70-foot tall gantry. So basically at sea with cable on the seafloor, we had to pick up that connector using the onboard crane and lift it about 90 feet above deck over the top of the gantry and lower it down onto the stern to deploy it off the stern chute. So as I said, this weighed about a ton. Because it's always the way it goes. We did this 4 times. The first 3 times, this always happened sometime between 2 and 4:30 in the morning, where everyone's always feeling at their best. And on the third time we did it, it was pouring with rain just to make it even more fun. The last one we did, it was about 10 o'clock in the morning and it was beautiful and calm and sunny, which is of course the way it goes. But here you can see literally this is it, almost at the top over the gantry. So you can see how high this 1 ton thing being lifted is. Lifting anything at sea is not an ideal thing to do. It's a high risk operation. This was definitely the highest risk operation of the whole of this project. However, it was very, very well planned for. I will say that for the RTKC guys, and it all went off flawlessly 4 times. So lowered down over onto the stern deck. Basically, they then secured that to a winch cable, a winch and a winch cable on the ship. Lowered the connector into the chute, and then lowered the connector all the way down to the seafloor. So at that stage, we had the cable on the seafloor, we had the connector on the seafloor, and the ship was connected to the subsea connector by a winch cable. So we weren't quite finished. And this is where the ROV came in. The ROV had done lots of operations, but basically the ROV came in, was sent down to the seafloor. This is from inside the ROV shack, them monitoring the operations. And then using a manipulator, it basically grabbed hold of a release for a ROV-friendly shackle. It would basically pull on that release and pop loose a spring-loaded pin and release the shackle. And at that point, the subsea connector is separate from the vessel. Cable lay is complete. Did that 4 times, leaving our connectors on the seafloor at about 260 feet of water, waiting for when we have a developer come in. The final step was the Nautilus, the cable burial vessel, 31 people on board, solely dedicated to the operation of this. And this is the CMROV-3, which is a cable maintenance, remotely operated vehicle, 12 feet by 12 feet by 9 feet, about 10 tons in air this thing weighs. And this is the cable burial, remotely operated vehicle. So it's a tracked ROV with these jetting arms that would basically follow the track of the cable, use jetting arms, cut a trench in the seafloor, and allow the cable to drop into that trench. Repeat that a couple of times, and that is how we got the cable buried. Just a picture of the control room for the CMROV and the sonar image at the bottom of them tracking the cable, and then just a couple of seconds of the sort of video footage that they were watching when they were doing this. So cable installation, the cable burial was completed October 13th, so a little late in the season. Conditions were beginning to deteriorate. This was a big operation. We had about 300 days of vessels on charter, about 5,000 person days for this cable installation operations. But with that, that was really the end of the construction piece. Since then, we have been busy preparing for developers coming in. We finished construction early this year. The last pieces were done. We've been putting agreements in place with the national labs who are our partners. We recently signed a power purchase agreement with Bonneville Power Administration, who will be buying the power that's generated at PacWave. So while it's very geeky and sort of a very energy industry thing, a power purchase agreement with Bonneville Power Administration is really quite a big deal. We also have an interconnection agreement with Central Lincoln PUD, who our power is going to go on to. For us, one of the really huge things with the current climate was in September, we actually got approval from the Department of Energy to move into our operational phase and received funding from the Department of Energy for the first 2 years of operation. So that was obviously very significant for us. Really sort of endorsement from the Department of Energy and the current administration for wave energy, hopefully moving forward and setting ourselves up to be prepared for our developers coming in. And that's what we've been preparing for. We're continuing to do environmental monitoring that's required for our permits, looking at organisms, acoustics. We're measuring wave and current data and preparing for these 3 companies who are currently funded by the US Department of Energy to come in and test. Their funding's on hold at the moment. So we're waiting for them to start moving again. But we have three companies. We have PacWave out of California with their X-Wave device. That's the only grid-connected device out of these three that's coming in. We have C-Power, who are a Virginia-based company, but all their engineering is done out of Corvallis. And then a team, the device is made by a company called Aqua Harmonics out of Portland, teaming up with Portland State University. And just a couple of pictures. This is the PacWave device. This is a smaller version that they just deployed off scripts a couple of years ago. The device they're going to be testing with us is larger. It's about 60 feet by 60 feet and weighs about 435 tons, to give you some idea of the scale of these devices. And that's a relatively small device. This is two of the C-Power devices. The top one is what they're going to come and test with us, a non-grid connected device, the C-Ray. I think it's about 25 feet across. And then the bottom one, the Stingray, is their conceptual utility scale device. And I believe that's going to be about 2,000 tons. So they're still in the design phase for that. They're not getting ready to test, but we may see that at PacWave at some point. So that's what we're doing, planning for the testing. What we're also doing now that we're operational is building partnerships. You know, one of the things recently, PacWave became part of Hatfield, which is fantastic. So what we're doing is working to build relationships with the Hatfield community, with the greater OSU community, with the national labs, and with industry. And while testing of wave energy devices is our primary function, we're also looking about how else can we use this open water test site. You know, there's opportunities for prototyping and testing of other types of technologies. There's experiential learning opportunities for students, for projects, for internships with some of these companies who are coming in, for having marine engineering courses based around what's going on. You know, there's no university that's got a living lab like PacWave is going to be once we have devices out there. So it's an exciting time, and we're sort of exploring all the opportunities that there might be. And then there's the research side, lots of research opportunities. We don't conduct the research, we help support the research. The idea is a lot of the research will be run by our affiliated organization, the Pacific Marine Energy Center. This picture's of Sarah Henkel, our benthic ecologist, who's based here, but lots of environmental monitoring, resource characterization, research on operation and maintenance, safety, grid interconnection, lots and lots and lots of opportunities. So moving into our operational phase, this is a really exciting time for PacWave after 12, 13, 14 years of trying to get here. And we're hoping in the next few years, the next year or two, you're going to start seeing devices out here. You're going to see exciting activity happening in Newport, up and down in Coos Bay, and everyone else, everywhere else, supporting operations at the test site. So there we are. A lot of stuff about PacWave. Our website, pacwaveenergy.org. And I would be more than happy to take any questions if people have any.
Wonderful. Thank you so much, Dan. We're going to bounce back and forth between questions online and questions in the room. And I can see already that Roseanne has a question for us online. Go ahead.
For this test site, the power was merged after reaching land because of having different partners. In the future, on a large site, would it also merge on land, or could it merge at sea to save on cable costs?
That's a really good question. Most likely you're going to see, like you do with offshore wind, is that assuming wave energy takes off, we will expect to see, you know, wave farms like you have wind farms and so on. And probably what you will see, because of the cost of subsea cables, what you probably will see is individual devices coming into a hub or you know, a central place where it will all come together and then run out of one or two export cables back to land. You know, cables are incredibly expensive. Our cables, our 47 miles of cables, were about $70 million. for the cables and the installation process. Cables are expensive. So yeah, definitely, smaller cables for the interconnection between devices coming into a central hub is likely to be the way it's going to be when we start getting towards, arrays of devices or farms. Yeah.
Questions in the room? All right, hang on a second.
What has been the impact of the current administration on this project, because they're not big fans of renewable energy, and what's the outlook on that?
Yeah, there was definitely a lot of uncertainty. Um, you know, the current administration is not a great fan of renewable energy. I think everyone's aware of that, but they particularly don't like wind and solar. Wave energy, we seem to be doing okay. There was an early executive order that came out that talked about the importance of capturing energy from the movement of water. And a lot of people read that as hydropower, but we are the marine energy falls within the National Hydropower Association because there's lots of similarities between marine energy and more traditional hydro. It's been a really good partnership because the National Hydropower Association is a very powerful group. Marine energy is not because we're very little. So that partnership's been good, and generally that's been pretty supportive from the current administration. There was a question when we were moving for our approval to move into our operational phase. We had to be approved by the Department of Energy. Normally, that decision would have been made at the director of the unit where our funding comes from. That decision had to be signed off by the Secretary of Energy, and we had no insight into what was happening there. And Secretary Wright signed off, gave us the approval, and our funding came through. There was uncertainty there. We didn't know if things were going to move ahead or not. I was cautiously optimistic. I talked to my previous boss, and she didn't think we were going to get approved. It was interesting. But at the moment, things are feeling pretty good. There seems to be general support. We don't seem to be in the crosshairs. The one thing, as I mentioned, is the developers who are lined up to come in at the moment, their funding is on hold. So we're liable to see delays in them getting in the water. But all the conversations we have, we were on the phone with Department of Energy today. The hope is that will start moving. At the moment, we're not targeted. So we're in a better position than a lot of other places are.
All right, other questions in the room?
I know this will surely vary based on what kinds of models are actually selected, but once there's actually a commercial scale, I guess, wave operation, what is the spacing between these units like? Like, is it going to be a couple 100 meters between or a mile, or do you have any idea of that?
It's going to vary a lot from device to device. It's not going to be a mile. With wind turbines, these things, even, when I mentioned the device that's like the sea power device that's potentially 2,000 tons, it's 150 feet tall, which is mostly submerged, and like 70 or 80 feet wide. So the footprints of the devices are much smaller. You don't have the massive sweeps of the wind turbines and so on. So they can be located much closer together. One of the things, there's sort of two ways of looking at this for the commercial scale wave. And again, we're not sure how it's going to go. But some companies are looking about big, 1 megawatt, 2 megawatt, whatever devices. And the sort of 2,000-ton devices. And then others are looking at a cluster of smaller devices coming into a central hub, 300 kilowatts. And then you have maybe 10 of them coming together. So you have 3 megawatts, but those things scale-wise are much smaller. And because they're coming into a central hub, co-locating them as much as possible is ideal, which means the footprint is a lot smaller. So it's until it sort of becomes clearer which direction the technology is going, it's difficult to answer, but it's not going to be the same spread that you see with offshore wind, I don't think.
So Dan, what does the anchoring systems look like? You didn't talk about whether you had anything set in place, or is that coming with each of the individual pieces of technology?
That's a really good question. That was something we thought long and hard about when we were developing the site and talked to a lot of developers. We do not provide any anchors. Part of it is the anchoring systems, the spacing of the anchors, everything else is very specific to the device and in a lot of cases is directly tied to the operational of the device. It's not just holding the device in place. So, putting in anchors is really expensive. Maintaining anchors is really expensive. And we didn't want to invest a lot of money in putting in anchors if, one, they were going to be in the wrong place, or developers wouldn't be able to or wouldn't want to use them. And we reached out to we did a survey of developers when we were in the design phase and talked about, permanent anchors. And they all said, we wouldn't use your anchors. When we've had a number of developers come in and we have an idea where people are deploying, if each of them's always putting one of their anchors in the same place, we may look at putting in some really big semi-permanent anchors. One of the things with our BOEM lease and our FERC licenses, when we're finished with PacWave, we have to remove everything from the seafloor. So we can't put in permanent anchors, but we could put in really oversized things that would definitely help the developers. But at this stage, it's on a developer having to install their anchors themselves.
So a follow-up question to that, the infrastructure here on the coast to be able to support the deployment of these type of things, can you talk about that?
Yeah, that is a challenge. That's one of the things we run into, even with the vessels that we were using for our cable installation. One of them came from, well, the cable burial vessel came from Spain. The cable lay vessel came from Louisiana, but there are some in Seattle. There are others down in California. There's not a lot of large, heavy vessel activity and capability on the West Coast at the moment. One of the things that was looking good was California was very interested in offshore wind, and that may take off. That will definitely increase the availability of vessels. There are vessels who are interested in coming to be based in the Pacific Northwest when PacWave takes off. But until there's business, they're not going to turn up. It's kind of, if you build it, they will come. We really hope so, because we're going to need those technologies. At the moment, for a lot of that expertise and equipment, they're going to have to mobilize it from a distance away. And that's really expensive. So building up the supply chain, building up the expertise, building up, working with companies who are going to become experts in handling our subsea connectors, that's all going to have to develop as the industry develops. And it's going to be interesting because there's a lot of interest, but there's a lot of interest saying, well, when are people coming? How much business is there going to be? We're very dependent at the moment on the flow of money from the Department of Energy, who's largely paying for these deployments. And it's kind of, we don't know. They're congressional appropriations each year. Who knows? So it's difficult. And it is, once we start having devices in the water and there's regular activity, I think we will see vessels moving into the area. I think we'll see expertise moving in. I expect we'll see ROV companies moving in and so on. But until there's activity going on, it's going to have to come from elsewhere.
All right, I see another question online. Go ahead, Roseanne.
In each of the 4 spots, is there space for one partner to trial multiple devices at once to practice multi-unit deployments?
That's a really good question. I realized after I was talked about it that I didn't cover that. So yes. So we have the capabilities, the size of our cables and the size of our sites, of our test berths offshore are designed to allow arrays of devices. A lot of people at the moment are looking at single device deployments because they're earlier, they're not at the stage of they're trying to prove whether their technology works, and they need to prove that on one device before they start spending the money on multiple devices. But ultimately, the next step is to have an array of devices, because people are not going to be deploying single devices. It's way too expensive. It is going to be small farms or even big farms at some point in the future. So we have the capability at our sites of supporting small arrays, potentially 3, 4, 5 devices in those berths.
All right, we got a question, Joe, all the way in the back. Yeah, meet me halfway.
Two questions. One, you mentioned that 2 out of the 3 potential companies that are going to be coming in had non-grid connected devices. And so what does that actually mean with respect to all the cabling you just put out? And then 2, again, with respect to the cabling, does the consumer here of the Central Lake PUD, will we actually see something like off our bill that is associated with what's coming in? Is that sort of what they're setting up? Or are they just taking the energy and we won't see anything come out from it?
So, okay, first question. So yeah, so we have 4 cables, 4 connectors out there to start off with. We're only going to have 1 cable being used. The idea is the next round, Department of Energy had a funding opportunity announcement for another 3 grid-connected companies to come in and test. That's on hold at the moment as well. But yeah, the idea is that we will build up to that. The 2 companies, Aqua Harmonics and Sea Power, they have future iterations of their devices that will be grid-connected, but the ones they have at the moment are not. Our infrastructure will sit there quite happily. It's not going to harm it. But ultimately, we want those cables to be used because there's been a lot of money invested in it. And what was the second question?
Income cost reduction for local.
Oh, yes. No. So the power that's been generated at the moment is going to be incredibly expensive. So Bonneville Power Administration is going to be buying power from PacWave at whatever it's tied to some index, but it's going to be a couple of cents a kilowatt hour. These companies are probably going to be generating power at 80 or 90 cents a kilowatt hour initially because it's a one-off technology and so on. So the actual cost to generate the electricity is really high. These companies are not doing it to make money at the moment. OSU, we're not making any money. It will be handed on to the developers. Central Lincoln PUD, we are paying Central Lincoln to offset any costs that they have for receiving our power because they're a public utility, so they can't be using Central Lincoln's money to support PacWave's operations. So we have a monthly fee that we pay Central Lincoln, which helps cover the engineering costs and metering costs. But at this stage, no, you're not going to see any reduction in electricity bills due to PacWave. You will be using some of the electrons that come from PacWave, but no, not at this point.
Great. Thank you. All right, we have run out of time already, Dan. So everybody in the room, why don't we give one more round of applause for Dan? And Dan has left his contact up in the corner of the slide. So if you have other questions or we weren't able to get to other questions online, feel free to reach out to Dan. Thank you all for being here. And please come back next week for our last seminar of 2025. Thanks, everyone. Thanks, Dan.
Thank you.